A function takes an input x and returns a new value, f of x. Usually, the output is different from the input. But there may be a special value that the function leaves unchanged. At this point, the input and output are exactly the same. This is what we call a fixed point. In symbols, a fixed point x star satisfies f of x star equals x star. But knowing what a fixed point is leaves a harder question. Can we actually find one by repeatedly applying the function? Start somewhere, and feed the output back as the next input. The iterates close in on the fixed point. Iteration becomes an algorithm. Does this always happen? Not necessarily. What property of the function makes this convergence reliable? Which number stays the same after we take its cosine? The curves cross once. That is x star, approximately 0.739. Can we reach it by iterating, the way we just did? Start at 0.2 and apply cosine. The output becomes the next input. Each step bounces vertically to the curve, then horizontally to the line. The iterates alternate around x star, and the jumps shrink every time. Was 0.2 special? Watch from 0.05, 0.5, and 0.9. Every path converges to the same point. Why does cosine pull different inputs together? Pick 2 points. Measure their distance. Apply cosine to both. The output distance is shorter. Try another pair. Same result. A contraction compresses distances by a uniform factor q, strictly less than 1. Not every map contracts. A map like 2x doubles every distance. The contraction property is doing real work. So why does cosine contract on 0 to 1? Cosine of 0 is 1. Cosine of 1 is about 0.54. The image sits inside the domain. The derivative of cosine is negative sine. On this interval, sine is positive and increasing, peaking at sine of 1. By the mean value theorem, the distance shrinks by at most sine of 1. That is q, approximately 0.84. Now we can state Banach's fixed-point theorem. If the space is complete, the function maps it into itself, and it contracts distances, then a unique fixed point exists and iteration converges to it. Complete means every convergent-looking sequence reaches a limit in the space. A closed interval qualifies. Our example passes all three. The gaps between consecutive iterates shrink geometrically. Each gap is at most q times the previous. So the iterates bunch into a Cauchy sequence. Completeness gives the limit. Contraction forces it to be a fixed point. Each step shrinks the error by at most q. After n steps, the error is at most q to the n times the starting distance. The theorem gives a computable bound. After 20 steps from 0.2, the error is guaranteed below 0.002. The actual error is about 0.00014. Why must the fixed point be unique? Suppose two exist. Both are fixed, so cosine leaves their distance unchanged. But contraction demands it shrink. Contradiction. The fixed point is unique. Banach's theorem does more than promise a fixed point exists. It gives a mechanism to find it, proves it is unique, and tells us how fast we approach it. All from a single inequality.